Let's continue this tutorial with a simple example. Our cost function is the sphere function. Sphere function is defined as the sum of the squares of the input values. If Vx is the cost function value, and x is a vector in d-dimensional space, where xi represents the individual components of the vector. Sphere function is frequently used as a benchmark function in optimization problems. Without loss of generality, and for the sake of simplicity in calculations and presentation, we will consider this function in 2 dimensions as shown here. In 2 dimensions, the sphere function can be visualized as a contour plot, where each contour line represents a constant function value. The contours are circular, indicating that the function is symmetric around the origin. Now, what is our goal? We want to find the lowest point on this surface. Okay, now, we're ready to take the algorithm step by step. First, let's take a look at the flowchart. In the first step, we look at the mathematical expression of the problem. Sphere optimization is equivalent to minimizing the following function. That is, finding the point where the function has the smallest value. We can also impose conditions. For example, the optimal value must be within a certain range. Okay, according flowchart, we should now prepare the inputs to the algorithm and initialize them. PSO optimization algorithm relies on a set of key parameters to control its behavior and effectiveness. Here, we will explore the most important parameters. First, we need to adjust the swarm size, referred to as npop. Npop indicates the number of particles in the swarm. For the sake of simplicity and ease of understanding, we will consider 5 particles. The second parameter is the number of iterations, max ITR, which is problem-dependent. We set it to 50 to avoid premature termination or unnecessary computational complexity. The next parameters are the limits on position and velocity. In PSO, it's essential to define the lower and upper bounds for both. For position, we set the bounds as smin equals -15 and smax equals 15. For velocity, the bounds are set to -3 and 3. The next key parameter is the inertia weight, W. It balances exploration and exploitation in PSO and influences the movement of particles. Typically, W is adjusted between 0.4 and 0.9, and we set it to 0.73. Finally, 2 other key parameters are the cognitive and social acceleration coefficient, which named as C1 and C2. The cognitive acceleration coefficient determines how much a particle's personal best influences its movement, reflecting the particle's tendency to learn from its own experience and move towards the best position it has encountered. The social acceleration coefficient influences how much a particle is guided by the global best in its movement, indicating the particle's tendency to follow the swarm's collective knowledge. We set both coefficients to commonly used values of 1.494. Okay, that's enough. We will learn more about these concepts later. Now, in the next step, we will initialize the particles. Each particle starts with a random position and velocity. For our problem where the cost function is the 2-dimension sphere function, the position has 2 elements in x and y direction. For example, the position of the ith particle, xi, is defined as a 2-dimensional vector. The same applies to its velocity. Each particle's position is randomly initialized within the defined limits using a uniform distribution. This means that each position within the specified range has an equal probability of being selected, ensuring a diverse spread of initial positions across the search space. In our problem, the position of each particle is initialized uniformly in range of -15, 15. Each particle's velocity is also randomly initialized within same range. After initializing the positions, the fitness of each particle is evaluated using the cost function, which, in this case, is the 2D sphere function. This evaluation helps determine how well each particle performs in relation to the optimization objective. This function measures the distance of the particle position from the origin. Here we can see how the cost of each particle is calculated. Now we have cost value for all particles. Okay, let's look at the flowchart again. After evaluating the cost function of each particle, the personal best and global best should be adjusted according to particles' cost values. Since the particles are in their initial stage, each particle's personal best position is set to its initial position. The global best position is initialized to the position of the particle in the swarm that has the best fitness value, specifically the particle with the lowest cost function and the shortest distance to the origin. Based on the calculated values, the fifth particle has the lowest cost and is selected as the global best. The surface and contour plot clearly indicate that the purple particle is closest to the origin. Once initialization is complete, we proceed to the main loop of the algorithm where the real action begins. This stage involves updating both the position and velocity of the particles. The update step in the PSO algorithm is crucial for guiding particles toward optimal solutions. These two updates may also be subject to specific conditions and restrictions. This iterative process enables the swarm to effectively explore the solution space and converge toward optimal solutions. We will further explore this process in the following sections.